The universe operates according to rules, fundamental rules. Rules so deeply embedded in the fabric of reality that we've come to accept them as immutable barriers on what is possible and what is not. But in 2019, a machine violated one of those rules so completely that almost nobody noticed. And when physicists did notice, everything changed. We tell the story of quantum computers all wrong. When we talk about them in the media, in classrooms, even in scientific journals, we frame the conversation in a single dimension: speed, faster calculation, better processing, engineering advances, a sleeker phone, a more powerful processor, just better. But this framing is fundamentally wrong, and it's wrong in a way that actually matters. Quantum computers are not faster in the way that a 2025 phone is faster than a 2015 phone. They are not an improved version of something that was already possible. They are not evolution, they are revolution, they are something different in kind. They operate on a principle that should not work, a principle so weird, so counterintuitive, that it seems to violate the basic rules of how machines function. And yet, they do work. To understand why this matters, we have to go back to 1985, not to some prestigious laboratory surrounded by colleagues, equipment, and institutional prestige, not to Silicon Valley, not to MIT, not to CERN. We go to Oxford, England, to a modest house, late into the night. There, a man sat alone, deliberately removed from the machinery of academic fame and recognition. His name was David Deutsch. And he was asking a question that no one else had quite managed to frame. It was not about speed, it was not about engineering. It was a question about the very nature of what computation could possibly be. Can we build a machine, he asked, that simulates any physical process in the universe with perfect accuracy? Not approximate it, not model it with useful simplifications, actually simulate it. Exactly, using the laws of physics themselves as the operating functions. This was not a question about being faster. This was a question about being fundamentally different, about doing something that should be impossible according to everything we thought we understood. When you ask the right question, sometimes the universe answers in ways that change everything. Deutsch's insight was revolutionary because it asked whether a machine could exist that was more powerful than the classical computers we had assumed were the ultimate form of computation. Whether nature itself could be harnessed as a computing substrate, whether the laws of physics, the very same laws that say certain things are impossible, could be weaponized to make those impossible things real. The implications were staggering. If Deutsch was right, if such a machine could theoretically exist, then it would mean that our understanding of computation was incomplete. It would mean that there were whole classes of problems that could never be solved by classical means, but which a quantum computer might crack. It would mean that the barrier between possible and impossible was not where we thought it was. For decades, this remained mostly theoretical. Fascinating to physicists and mathematicians, but impractical. Unrealistic. A beautiful idea that could never really work. And then 2019 happened. Then a quantum computer actually did something remarkable. Something that classical computers could not easily do. Something that made people sit up and take notice. Something that made the theoretical suddenly very real. The machine that did this was not magic. It did not violate the laws of physics. Instead, it obeyed them in ways that nobody had quite figured out how to use before. It operated according to quantum principles that seemed to defy our intuition about how the world works. It used superposition and entanglement and interference patterns to explore vast possibility spaces simultaneously. And it returned an answer that classical machines would have required eons to find. This is what changes everything, not the speed, not the processing power, but the fact that we can now harness quantum mechanics itself as a tool, that we can bend the strange rules of the subatomic world to our purposes, that what seemed impossible is merely improbable, and what we thought we could never do, we can now actually accomplish. David Deutsch dreamed alone in Oxford, and from that dream emerged a new way of thinking about computation. From that dream emerged machines that should not work, but do. From that dream emerged the beginning of an answer to one of the most profound questions we can ask. What is actually possible in this universe? What are the real limits? And how far beyond what we thought were the barriers can we actually go? The answer, it turns out, is much further than we imagined. And to do that, we have to go back to 1935, to a physicist named Erwin Schrödinger sitting down to write what he believed was a definitive critique of quantum theory. Schrödinger was not trying to contribute to the field, he was trying to destroy it. He was trying to prove that quantum mechanics was internally inconsistent, that it made predictions that violated basic logic. The problem Schrödinger identified was this. Quantum mechanics says that particles do not have definite properties until they are measured. Before measurement, a particle exists in what physicists call a superposition, a combination of all possible states simultaneously. The particle is not in one state or another. It is in both at once. This seemed to Schrödinger not like clever physics but like absurdity. A particle cannot be in two places at once. An electron cannot be spinning both up and down at the same time. This violates basic logic. So Schrödinger designed a thought experiment to expose this absurdity. He imagined a cat sealed in a steel box. Inside the box is a radioactive atom and a mechanism that will kill the cat if the atom decays. Quantum mechanics says the atom is in a superposition of having decayed and not having decayed. Therefore, the cat must be in a superposition of being dead and being alive. Schrödinger meant this as a reductio ad absurdum. Surely, he reasoned, this proves that something in quantum mechanics must be wrong. What happened instead was that physics spent the next 70 years confirming quantum mechanics with greater and greater precision. Decade after decade, experiment after experiment, more accurate, more detailed, more comprehensive. The cat thought experiment did not break quantum mechanics. It became its most famous illustration of how deeply weird quantum reality actually is. And here is the connection to what Deutsch built. A qubit, the basic unit of a quantum computer, works exactly like the atom in Schrödinger's box. It is not a zero, it is not a one. It is both at the same time until the moment you measure it. And while it is in that superposition state, it performs calculations across all its possible values simultaneously. This is not speed in the classical sense. This is not parallel processing like a regular computer with multiple cores. This is something fundamentally different. This is the ability to exist in multiple states at once and extract results from all of those states before collapsing into a single answer. This is the source of the power that we could not explain in conventional terms. Not faster computation, not cleverer engineering. The ability to be in multiple places at once and compute in all of them simultaneously. But this raises a question that almost nobody asks out loud. If a qubit is genuinely in multiple states at the same time, if the superposition is real and not just a mathematical convenience, what is it doing between measurements? What is happening in that space between the question and the answer? What is occurring when we are not observing it? And if this is not a simplification, if the qubit is literally in multiple states at once, what does that tell us about the nature of reality in the moments when we are not looking? Schrödinger would find this deeply uncomfortable, which is somehow exactly the right response to have when confronting the actual structure of reality. Now comes the number that changes everything: 300. If you build a quantum computer with 300 qubits, the number of simultaneous states it can hold is 2 to the power of 300. Write that out in full. 2 followed by 90 zeros. That number is larger than the total count of atoms in the entire observable universe. Every atom in every star in every galaxy we have ever detected. Every atom in every galaxy we have theorized about but not yet found. And this machine with 300 qubits still has more computational space than all of that combined. You cannot fit that computation inside one universe. There is simply not enough physical room. This is not philosophy, this is not metaphor, this is counting. Pure arithmetic. If you need to store and work with more computational states than your universe contains particles, you are by definition using resources from somewhere beyond your universe. That is not a theory. That is a necessity. Deutsch looked at this arithmetic and asked the only logical question available. Where does this computation happen? Where is the work being performed? And his answer was unavoidable. The computation happens across parallel versions of reality. Many worlds, many instances of the same machine, each exploring different paths through the solution space, then combining their results through a process called interference into a single answer that comes back to our reality. The quantum computer is not a faster calculator. It is a device that coordinates work across multiple realities and returns the results to this one. It is a bridge between branches of existence. And we built it. This machine sits in a refrigerated chamber, colder than anything that exists naturally in the observable universe, colder than the deepest reaches of space, colder than anywhere in nature has ever been. And it is doing something that, by the counting logic of our universe, should be physically impossible. It is performing calculations that require resources that do not exist in this reality. It requires parallel worlds to function. And it works. Think about what this actually means. We have built a human-made object that reaches beyond the boundary of everything we can observe. It is the first machine in human history to interact in a functional and measurable way with something outside of observable physical reality. The first time we have built a bridge to somewhere we cannot see and used that bridge to get answers. And then the question becomes, what else is on the other side of that bridge? What was already there before we knocked? What are we interacting with when we run these machines? The man whose mathematics made all of this possible died before he ever knew that his idea would become the foundation of something world-changing. His name was Hugh Everett III. He was a graduate student at Princeton in 1957 when he submitted his doctoral dissertation. His idea was radical and strange and far ahead of what the physics community was willing to accept. Everett proposed what he called the many worlds interpretation of quantum mechanics. The idea was this: when a quantum system is measured and appears to collapse from a superposition into a single outcome, that collapse does not happen because one outcome is selected and the others disappear. All outcomes happen. Reality branches. Every possible result occurs in its own version of the universe. The cat is alive in one branch and dead in another. Both branches are equally real. There is no collapse. There is only multiplication. The universe does not choose. It splits. Everett submitted this interpretation to the physics establishment in 1957. The response was swift and dismissive. Niels Bohr, who at that time was the most powerful voice in quantum physics, dismissed the idea. The community followed Bohr's lead. Everett's dissertation was accepted, yes, but his interpretation was treated as a curiosity at best and an embarrassment at worst. A strange idea from a young person who did not yet understand how the field actually worked. Everett left academic physics immediately after receiving his degree. It is what survives after everything incorrect has been systematically eliminated by the physics of the computation itself. The machine is not selecting the right answer. It is creating conditions where wrong answers cannot survive. It is like the universe itself is doing the selection, like physics is doing the filtering. The structure of the computation itself ensures that only correct answers remain standing. I find this almost difficult to accept as a description of a machine that physically exists. It is not selecting, it is eliminating, which raises a question about the nature of computation itself. Is this how reality works more broadly? Is the physical world we experience the result of a similar process, where most possible configurations cancel out and only certain stable patterns survive long enough to be observed? And if so, what does it mean that we built a machine that deliberately replicates that process? Are we computing? Or are we doing something closer to what the universe does to produce reality in the first place? In 1994, a mathematician named Peter Shor, sat down and worked out something that most of his colleagues assumed was impossible. He wrote an algorithm, a set of instructions that a quantum computer could follow to break apart any large number into the prime numbers that multiply together to produce it. On the surface, this seems like an abstract mathematical exercise, a curiosity, something with no obvious connection to anything that matters in the real world. But the connection becomes visible the moment you understand how the internet works. Almost all of the encryption that protects the modern world is built on a single assumption. The assumption that multiplying two large prime numbers together is easy, trivially easy. But working backwards from the result to find the original prime numbers is practically impossible. It would take a classical computer thousands or millions of years. The information would be worthless long before the lock was broken. That assumption is the foundation. It is the bedrock. It is the reason why your bank account is separate from everyone else's. It is why private communications stay private. It is why governments can encrypt their secrets. It is why hospitals can protect patient data. The entire cryptographic architecture of the modern world is built on the assumption that this reversal is not feasible. Peter Shor proved that it is feasible. A sufficiently powerful quantum computer running Shor's algorithm could factor large numbers not in thousands of years but in hours, possibly minutes. The entire structure collapses. The mechanism that protects everything becomes useless. The machine just does not exist yet, at the required scale. But we have already established that the machines are growing exponentially, and the growth is accelerating. And nobody can say with certainty when the threshold will be crossed. This is the place where the abstract becomes uncomfortably concrete. Everything encrypted today is potentially being stored by anyone with the resources to store it. Governments, private actors, foreign powers, anyone waiting for the moment when the machine becomes powerful enough to open it. The term people in cryptography use for this is harvest now, decrypt later. You collect the encrypted data today. You store it. You wait. The lock will eventually open. And when it does, everything inside becomes visible. Every secret, every private communication, every piece of information that was protected only by the assumption that the key was unbreakable. We have had 30 years to think seriously about this. Since 1994. 30 years. And the infrastructure has not fundamentally changed. Most of the encryption protecting modern civilization is still based on mathematical difficulty, still based on the assumption that Shor proved was breakable. What does that say about how we respond to threats that arrive slightly ahead of their consequences? What does it tell us about our ability to act on information that is theoretically known but not yet practically urgent? And what other assumptions are we currently living inside of that someone has already worked out how to break? What other mathematical assumptions are currently protecting things we care about that have been proven to be fragile, and we just do not know it yet? There is a particular kind of institutional signal that is easy to miss if you are not looking for it. It is not a press release. It is not a headline. It is a government agency quietly spending years and significant resources solving a problem that officially does not exist yet. In 2016, the National Institute of Standards and Technology launched a competition. They invited mathematicians and cryptographers from around the world to submit new encryption algorithms, not improved versions of existing ones, not tweaks or optimizations. Fundamentally different ones, built on mathematical problems that a quantum computer running Shor's algorithm could not break. 82 teams from 25 countries submitted proposals. The competition ran for 8 years. The final standards were published in 2024. Think about what this sequence of events actually communicates. A government body does not spend 8 years and coordinate 82 international teams to solve a hypothetical problem. They do not publish binding standards for a threat that exists only in theory. The implicit message inside the entire structure of that competition is this: The people with access to classified information about the state of quantum hardware believe the threat is real, believe the threat is coming, and believe it is coming on a timeline that requires action now. Not in 50 years, not in a decade, now. The public conversation about quantum computing tends to treat it as a future problem. Something to think about eventually. Something that will matter to our grandchildren. The NIST competition is institutional proof that some very serious people do not share that timeline. And here is the layer underneath that which I find harder to set aside. The competition was launched in 2016. The standards were published in 2024. The systems that need to be updated to use those standards, the actual infrastructure of the internet, banking, government communications, will take years more to retrofit. Which means there is a window, a gap, a period of vulnerability. The gap between when the quantum machines become capable enough to break current encryption and when the new encryption is actually installed everywhere. How long is that window? How wide is it? Nobody knows exactly. And who right now is paying very close attention to its edges, who is watching that gap close and preparing to exploit it. Who has the machines and is waiting for the moment when they become powerful enough to use. John Wheeler spent 60 years working at the center of theoretical physics. He coined the term black hole. He worked with Niels Bohr on nuclear fission. He supervised the doctoral dissertations of Richard Feynman and Hugh Everett. By the time he reached the end of his career, he had spent more time thinking seriously about the foundations of physical reality than almost anyone in human history. And the conclusion he arrived at was this: information is not something that the universe contains. Information is what the universe is made of. He called it from bit. The idea is this: every particle, every field, every physical thing that exists gets its existence, its properties, its reality from answers to yes or no questions. Does the electron spin up or spin down? Did the photon pass through the left slit or the right slit? Is the atom here or there? Wheeler argued that the physical world is not the primary thing, with information layered on top of it. The information is primary. The physical world emerges from it. This is a genuinely strange idea to sit with, because it inverts the intuition most of us carry around without examining it. We tend to think of reality as the solid ground and information as something we extract from it, like harvesting wheat from a field. Information is the secondary thing, the property, the description. Wheeler is saying the field is made of wheat all the way down. There is nothing underneath the information. The information is the ground. Now bring that idea into contact with what we have been building toward. If the universe is made of information, then a device that manipulates information at the most fundamental physical level is not modeling reality. It is not simulating reality. It is operating on the actual substrate from which reality is constructed. Every calculation a quantum computer performs is an intervention in the informational fabric of the universe itself, not a poetic description. If Wheeler is right, it is a literal statement of fact. And Wheeler is not a fringe figure making a provocative claim for attention. He is one of the most respected physicists of the 20th century, drawing a conclusion from a lifetime of looking at the deepest structure of things. From decades of thinking harder about the foundations of reality than almost anyone else who has ever lived. What does it mean to build a tool that works at the level where reality is being assembled? What else happens at that level that we have not yet thought to look for? And if the universe is information processing itself into existence, what are we doing? When we add our own processing to that conversation, when we run quantum computers, are we just computing? Because the alternative branches are simply not accessible to a surviving observer's experience. The observer cannot experience their own non-existence. Tegmark extended this to civilizations. In the many worlds framework, every civilization that could be destroyed by any quantum event has branches where it survives, no matter how improbable. The civilizations that exist to observe anything are the ones in the survivor branches, the ones where luck held, the ones where disaster was averted. the ones where they made it through. Now bring this back to Fermi. We look at the universe and see silence. We assume this means most civilizations fail. We assume that civilizations tend not to survive. But in the many worlds framework, the civilizations that survive are in branches where they survived against all odds. And those branches may look exactly like ours. The silence is not evidence that civilizations typically fail. It is evidence that we are in a branch where we have not yet encountered the ones that succeeded. Where are they? In the other branches. And what did they build when they got there? What do civilizations that survive look like? What technology do they develop? What do they become? And are they still becoming? Or have they already arrived somewhere we cannot see? In 2026, Seth Lloyd at MIT published a calculation that puts a hard number on something that had previously been discussed only in qualitative terms. He calculated the computational capacity of the observable universe. The answer he arrived at is approximately 10 to the power of 120 operations performed over the entire history of the cosmos, using every particle and every interaction as a computational resource. 10 to the 120, 10 followed by 119 zeros. Every electron, every photon, every quark performing its quantum interactions is, in Lloyd's framework, executing a computational operation. The universe is not like a computer. It is one. It has been running a single program since the Big Bang, using every physical interaction as a step in the calculation. Every event that has ever happened is a computation. What the universe is computing is an open question. Lloyd does not answer it. He simply establishes that the question is legitimate and that the scale is definite. The universe is large enough to run a very long computation, large enough to compute almost anything, large enough to compute us. Now place our quantum computers inside this picture. We are building devices that operate on the same physical principles as the universe's own computation. They use the same quantum mechanical rules, the same entanglement, the same superposition, the same interference. They are not modeling the universe's computation from outside. They are participating in it, adding their operations to the total, becoming in a small but physically real sense part of the universe's ongoing calculation. Which raises a question I do not have an answer to, and that I think deserves more attention than it gets. If the universe is computing something, and we add our own quantum computation to that process, do we change the output? Is the trajectory of the universe's calculation altered by what we compute inside it, and if so, in what direction are we pushing it? What is the effect of our computations on the computation that is the universe? Are we helping? Are we hindering? Are we changing the answer? Are we part of the solution or part of the problem the universe is trying to solve? Hugh Everett left academic physics in 1957, the year his dissertation was dismissed, and never returned. He went to work at the Pentagon, building mathematical models for nuclear targeting strategies. He was good at it. He was good at most quantitative things, good at math, good at calculation, good at reducing complex things to numbers. But his life was difficult. He drank heavily throughout his adult life. He smoked constantly. He told his family that he believed the many worlds interpretation was correct, and that therefore death was not an ending, but a branching. That some version of him would always continue in some branch of reality. Somewhere. Somehow. He would never fully die, because reality splits. Because he would always survive in some branch. Because death requires that all branches end. And that is impossible. His daughter Elizabeth wrote in her diary as a teenager that she wanted to commit suicide and meet her father in a parallel universe. She later struggled with mental illness for years, the weight of having a father who was brilliant and broken and absent, who believed he was immortal because reality split, who drank himself toward death while believing he could never fully die. His son Mark became a musician, formed a band called Eels, and has spent his career processing the experience of growing up with an absent, brilliant, broken father, writing songs about the pain of having a father who was there and not there, present and absent, alive and unreachable. Hugh Everett died in 1982 on his couch of a heart attack. He was 51. By his own request, his body was cremated and his ashes were thrown in the trash. Because in the many worlds interpretation, it did not matter what happened to any particular physical configuration. Somewhere in some branch, he is still alive. Somewhere he is watching the technology built on his mathematics become the most consequential engineering project of the 21st century. Somewhere he is observing the machines that require his interpretation to function. Somewhere he is vindicated. And somewhere he is still broken and alone on his couch. The many worlds interpretation he proposed in that dismissed dissertation is now cited in the engineering documents of companies worth hundreds of billions of dollars. The idea Bohr rejected is the idea the machines require. The theory that was too strange is the theory that is too fundamental to avoid. What does it mean that the people who build the future so rarely get to see it? And what does it mean that the branch, wherever it was believed, turned out to be this one? Somewhere in the multiverse, Everett is getting the recognition he deserved. Somewhere he is celebrated. Somewhere he is happy. But he is not here. David Deutsch does not fly on airplanes. He rarely leaves Oxford. He works at night. He has described himself as someone who finds it easier to think about abstract structures of reality than to navigate the practical requirements of ordinary social life. He is also, by most accounts of people who work in quantum computing, one of the 2 or 3 people most responsible for the fact that quantum computers exist as a field of inquiry at all. His 1985 paper laid the theoretical architecture. His subsequent work on the constructor theory of information has continued pushing at the same question from different angles for 40 years, turning it around, looking at it from new perspectives, trying to understand it more completely. What I find striking about Deutsch is not the eccentricity, which is common enough among theoretical physicists, but the completeness of his conviction. He genuinely believes that the many worlds interpretation is correct. Not as a working assumption, not as a useful framework, as a description of actual reality. He believes that when a quantum computer runs, the computation happens across a vast number of parallel versions of the universe simultaneously, that those parallel instances are as real as this one, that the machine is genuinely reaching into that parallel structure and extracting answers. He believes this the way most people believe that the chair they are sitting on is real, with the absolute confidence of direct perception, with the certainty of something known from the inside. And the machine he helped design works. It gives correct answers. It outperforms classical computers on problems that can be independently verified on small scales. So the question becomes, if the machine works and the only coherent explanation for why it works requires parallel universes, what exactly is the reasonable position to hold about parallel universes? How can you deny what the evidence clearly shows? And what does it mean that the man most responsible for the machine has held that position quietly from a house in Oxford for 40 years, watching the world slowly come to accept what he already knew, waiting, thinking, waiting for the machines to become powerful enough that the implications become impossible to ignore? In December 2023, IBM unveiled a processor called Condor with 1,121 qubits. In 2019, Google's Sycamore had 53. In 4 years, the number of qubits in a leading processor grew by a factor of more than 20. That rate of growth is not linear. It is not even cleanly exponential in the way Moore's law described transistor growth. It is faster than the projections that most quantum computing researchers were making in 2015. The number of qubits is not the only metric that matters. Error rates, connectivity between qubits, the depth of circuits that can be run before decoherence destroys the computation. All of these matter as much or more. But the trajectory of qubit counts as a signal about the investment and engineering momentum behind the technology. And investment and engineering momentum have a way of compounding in ways that are difficult to predict from the current position on the curve. The history of exponential technologies is a history of underestimating the back half of the curve. We are good at predicting the next doubling. We are poor at predicting what the 15th doubling looks like from the third. We are good at local extrapolation. We are bad at global prediction. We look at the current trend and assume it continues smoothly. We do not anticipate the moments when the curve suddenly changes trajectory, when it suddenly accelerates, when it suddenly becomes something other than what we expected. 15 doublings from 53 qubits is approximately 1.7 million qubits. Most estimates place the threshold for breaking RSA 2048 encryption somewhere between 1 million and 4 million physical qubits depending on error correction requirements. The arithmetic is not a prediction, it is a rough triangulation. But rough triangulations have a way of becoming more precise as the data points accumulate. What does the curve look like at doubling 20? And who is watching that curve most carefully right now? Who is betting on the exact point where the threshold will be crossed? Who is preparing for the moment? Or are we changing the nature of the computation that the universe is doing? The year after Wheeler published his framework, a physicist named Ralph Landauer at IBM Research had already, 30 years earlier actually, provided experimental proof that Wheeler's intuition was pointing towards something physically real. In 1961, Landauer published a paper arguing that information is not abstract, it is physical, and he had a specific measurable way to demonstrate this. When you erase a single bit of information, you release heat, not metaphorically, not as an analogy, literally. The act of taking a system that holds a 1 or a 0 and resetting it to a known state releases a tiny but measurable and theoretically unavoidable amount of thermal energy into the surrounding environment. This became known as Landauer's principle. Information is physical. Erasing it has a thermodynamic cost. For decades, Landauer's principle remained a theoretical prediction without direct experimental confirmation. Then, in 2012, a team led by physicist Eric Lutz built an experiment delicate enough to actually measure it. They trapped a single microscopic particle in a laser-generated well. They manipulated it to erase one bit of information, and they measured the heat released. The result matched Landauer's formula exactly. Thinking, at the most fundamental level, generates heat. Not because computers are inefficient and produce waste, but because erasing information is physically irreversible. And irreversibility has a thermodynamic cost that cannot be designed away. Every thought has a price. Every calculation leaves a physical trace in the universe. Now connect this back to quantum computers. A quantum computer operating in superposition is in a certain sense not yet committing to answers. It is holding multiple possibilities open simultaneously before collapsing into a result. Some researchers have suggested this might allow quantum computations that approach a kind of reversibility that classical computation cannot achieve, potentially sidestepping some of Landauer's heat cost. If that is true, then quantum computation is not just faster. It is operating closer to the theoretical minimum energy cost that physics allows. It is computing in a way that is more aligned with how the universe itself processes information than anything we have built before. What does it mean to build a machine that generates less heat than thought? What is the relationship between the cost of computation and the nature of the reality inside which that computation happens? What else is possible when you compute at the edge of physical efficiency? In 1935, the same year Schrödinger was writing his cat thought experiment, Albert Einstein co-authored a paper with Boris Podolsky and Nathan Rosen that was intended to accomplish the same goal, not to contribute to quantum mechanics, to bury it, to prove that it was fundamentally wrong. The paper described a scenario that Einstein believed revealed a fatal flaw in the theory. Imagine two particles that interact and then fly apart in opposite directions. Quantum mechanics says that certain properties of these particles are not determined until measured. But it also says that once you measure one particle, the other instantly takes on a complementary value, no matter how far apart they are. Measure the spin of particle A and find it pointing up. Particle B will instantly be found pointing down. Instantly. Regardless of whether B is in the next room or on the other side of the galaxy. Across light years of space. The correlation is instantaneous. Einstein called this spooky action at a distance. He found it not just strange, but physically impossible. Nothing can travel faster than light. If measuring particle A instantly affects particle B across any distance, that would seem to require either that information travels faster than light, which Einstein's own relativity forbids, or that the two particles were somehow carrying hidden information from the start. Predetermined values that just looked random until measured, like two gloves from the same pair. One spinning up, one spinning down. Always. Predetermined from the moment they separated. Einstein preferred the second explanation. He called the missing information hidden variables. He was sure they existed. He was sure quantum mechanics was incomplete. He was sure he had found the fatal flaw. He was wrong. Not probably wrong, not arguably wrong, experimentally, measurably, definitively wrong, in a way that took another 30 years to prove. And that still feels strange to confront directly. The property that Einstein dismissed as impossible, the instantaneous connection between separated particles, is called quantum entanglement. It is real. It has been confirmed by increasingly precise experiments over more than half a century. And it is one of the primary physical resources that quantum computers use to perform calculations that classical computers cannot. The thing Einstein invented as an argument against quantum mechanics became a tool inside quantum computers. I keep thinking about what that inversion means. The greatest physicist of the 20th century looked at entanglement and saw an absurdity, a sign that the theory must be wrong. The engineers of the 21st century looked at the same phenomenon and saw a computational resource. What does that say about the relationship between physical intuition and physical reality? And what other phenomena are we currently dismissing as impossible that someone somewhere is already figuring out how to use? Einstein died in 1955, still believing that hidden variables existed, still believing that entanglement was not real spooky action, still believing his interpretation was correct, still unable to accept what quantum mechanics was telling him about the structure of reality. And he was wrong. Beautifully, completely, definitively wrong. And we use the mechanism he dismissed as impossible to build the machines that will define the next era of technological development. In 1964, a physicist named John Bell working at CERN found something that changed everything. He discovered that the two pictures, Einstein's hidden variables and quantum mechanics, entanglement, make predictions that are numerically different, not philosophically different, not interpretively different, different in a way you can measure with instruments, different in a way you can test. He calculated a precise statistical boundary. Above that boundary, Einstein wins. Below it, quantum mechanics wins. The experiment had been waiting all along. Someone just needed to find the number. What strikes me about this moment is how long it took to realize the question was answerable at all. How many other questions are we currently treating as permanently philosophical that actually have a clean, physical answer sitting inside them waiting for someone to find the right number? In 1982, a 34-year-old French physicist named Alain Aspect ran Bell's experiment cleanly enough to settle the question. He worked at the Institut d'Optique outside Paris. The experiment he designed was technically demanding. He created pairs of photons, particles of light, in a way that entangled them. He sent each photon in a pair flying in opposite directions toward detectors. At the last possible moment, while the photons were already in flight, he randomly switched the orientation of the detectors. This last-minute switching was crucial. It closed a loophole that earlier experiments had left open. If the detectors had fixed orientations, a skeptic could argue that the photons had somehow learned the detector settings before they left and encoded that information in their hidden variables. by switching the settings after the photons were already traveling. Aspect made that explanation physically impossible. The photons could not have known, and the results came back unambiguous. The correlations between the two photons exceeded Bell's limit. Not slightly. Clearly. Unmistakably. Einstein's hidden variables cannot explain what Aspect measured. The universe is not locally real in the way Einstein assumed. Two particles can be separated by any distance and remain connected in a way that has no classical explanation, no classical parallel, no way to understand it within the framework of physics as it was understood before quantum mechanics. The Nobel Prize in Physics in 2022 went to Aspect together with John Clauser and Anton Zeilinger for this work. 40 years after the experiment, physics moves carefully when the implications are large enough. And the implications here are large because what Aspect proved is not just that quantum mechanics is correct. He proved that the world is structured in a way that our everyday intuition about separation and distance and independence simply does not apply at the fundamental level. Two things can be arbitrarily far apart and still be in some physically meaningful sense one thing. Now ask yourself what that means for a computer that uses entanglement as a computational resource. It is not just using a quirk of physics. It is using the deepest architectural feature of reality. What else is built on that architecture that we have not yet learned to use? And what changes when the machines that exploit that architecture become powerful enough to do things we cannot yet predict? In 1993, a group of 6 physicists published a paper with a title that sounds like science fiction and contains no fiction at all. The paper was called Teleporting an Unknown Quantum State via Dual Classical and Einstein-Podolsky-Rosen Channels. What they described was a procedure for transferring the complete quantum state of a particle from one location to another without moving the particle itself. Not the particle, the information that defines it. Everything about it. Every quantum property that makes it what it is, transferred completely. The procedure requires 3 things. A pair of entangled particles shared between the sender and receiver. A classical communication channel. An ordinary phone line or radio signal operating at or below the speed of light. And the original particle whose state you want to transfer. The sender performs a measurement that links the original particle to their half of the entangled pair. They send the result of that measurement through the classical channel. The receiver uses that result to perform an operation on their half of the entangled pair. And at the end of this procedure, the receiver's particle is in exactly the quantum state that the original particle was in. The original particle no longer holds that state. It has been transferred. In 1997, Anton Zeilinger performed the first experimental demonstration of quantum teleportation in a laboratory. In 2017, a Chinese team used a satellite called Mikius to teleport a quantum state from a ground station in Tibet to the satellite orbiting 1,400 kilometers overhead. The distance is almost beside the point, because entanglement does not weaken with distance. But it matters as a demonstration that this is not a laboratory curiosity confined to a controlled room. It works at the scale of the planet. It works at orbital distances. It works. And if it works for quantum states, what else can be transferred? What else can be teleported? If information can be moved without the physical substrate, what is the relationship between information and matter? Here is where the spiral tightens. Quantum teleportation does not move matter, it moves the information that defines quantum states. And if Wheeler is right, if information is the primary substance of reality, then quantum teleportation is not moving a description of something. It is moving the thing itself, leaving behind only an empty shell. What does it mean that we can relocate the informational identity of a physical object while leaving its physical substrate behind? Is the object the matter, or is it the information? And if it is the information, what are we when we are moved? What is the essential thing that gets transferred when you teleport? And what is left behind? There is an idea in theoretical physics that sounds on first encounter like a metaphor so extreme that it cannot possibly be meant literally. It is meant literally. The idea is called the holographic principle, and it emerged from the work of two physicists, Gerard T. Hooft and Leonard Susskind, during the 1990s. Here is the core of it. Imagine a region of space, any region, a sphere, say, with a defined volume. The holographic principle states that the maximum amount of information that can be contained inside that sphere is not determined by its volume. It is determined by the area of its surface, not the inside, the boundary. Think about what that means physically. You would expect that doubling the volume of a region would double the information it can hold. More space, more room for stuff, more information. But the holographic principle says no. The information capacity scales with the surface area, not the volume, which implies something deeply strange about the relationship between the inside and the outside of any region of space. All the information describing everything that happens inside the volume is somehow encoded on the two-dimensional surface surrounding it. The interior is not the primary thing. The boundary is. This is not a philosophical suggestion. T. Hooft and Susskind were not writing poetry. They arrived at this from rigorous calculations about black holes and thermodynamics. The principle has since become one of the most productive frameworks in theoretical physics, connected to string theory, connected to the nature of black holes, connected to quantum gravity. And it connects directly to what we have been building toward because of what it implies about the relationship between information and space. If the three-dimensional world inside a volume is fully described by a two-dimensional surface, then space itself may be a kind of projection, not an illusion exactly, but something more like a derived object. Something that emerges from a more fundamental layer of information encoded elsewhere. Which means that when a quantum computer manipulates information at the most fundamental physical level, it may be operating at a layer of reality that is more basic than space itself. Not inside space, underneath it. Operating at the level where space is being generated. Read that sentence again slowly. A quantum computer may be operating at a layer of reality more basic than space itself. Not underneath the laws of physics, more basic than the structure in which physics operates. More fundamental than the geometry that space and time are made of. And then I think the right question is this. If space emerges from information, what else emerges from information that we have been treating as foundational? What are we standing on exactly? And how stable is the ground when you understand what it is made of? What other structures that we assume are fundamental are actually emergent? What else appears solid only because we have not looked at what it is made of? If information is the fundamental substance of reality, then there is one question that follows immediately. And Stephen Hawking spent the last 40 years of his life wrestling with it. Can information be destroyed? The reason this matters is not abstract. If information can be destroyed, then the universe is not a closed system with a fixed amount of informational content. Things can simply cease to exist in a way that leaves no trace. Completely, utterly, gone. And if that is true, then the foundations of quantum mechanics, which assume that information is always conserved, always recoverable in principle, are fundamentally wrong. Hawking entered this question through black holes. In 1974, he proved mathematically that black holes are not the permanent objects they appear to be. They slowly radiate energy, a process now called Hawking radiation. And over vast timescales, they shrink and eventually vanish, completely disappear. The radiation they emit appears to be completely random. It carries no information about what fell in. A library could fall into a black hole. A hard drive containing the complete works of civilization, the sum of human knowledge. And the radiation that eventually comes out would look identical to the radiation from a black hole that swallowed only hydrogen gas. Indistinguishable. The library is gone. Not transformed. Not encoded somewhere. Gone. And with it goes all the information it contained, lost forever. This created what physicists call the black hole information paradox. And it turned into one of the longest and most heated arguments in modern theoretical physics. On one side, Hawking insisting that information is lost and quantum mechanics needs to be revised. On the other side, almost everyone else in the field insisting that information cannot be destroyed and that Hawking's calculation must be missing something. Decades of argument, decades of competing theories, decades of trying to figure out what happened to the information. In 2004, Hawking publicly conceded. He announced at a conference in Dublin that he had been wrong, that information is preserved somehow. And he paid off a bet he had made with the physicist John Preskill by giving him an encyclopedia. But the how of information preservation in black holes remains genuinely open. Nobody has a complete answer. The mystery remains unsolved. And the reason this connects directly to quantum computing is this. If information is always preserved, always conserved, always recoverable in principle, then every quantum computation leaves a permanent physical trace in the universe. Nothing computed is ever truly erased. Every calculation we have ever run, every result we have ever generated, every answer that has ever come out of a quantum computer still exists somewhere in the structure of reality. The information is still there. It did not vanish. It cannot vanish. What does it mean that every calculation we have ever run still exists somewhere in the structure of reality? And what does it mean that we do not know where? What does it mean to compute something and have that computation be forever part of the universe? What does it mean to leave that trace? Where does it go? Who might find it? What could they do with it? In 2013, two of the most respected theoretical physicists alive published a short paper with a title that looked like an equation. ER equals EPR. The ER refers to Einstein and Rosen, who in 1935 described a theoretical connection between two black holes, a tunnel through spacetime, now called a wormhole or an Einstein-Rosen bridge. The EPR refers to Einstein, Podolsky, and Rosen. The same year, the same Einstein. Describing quantum entanglement in the paper we talked about earlier, Juan Maldacena and Leonard Susskind were proposing something that sounds at first like wordplay. They were suggesting that these two phenomena, wormholes and entanglement, are not just analogous. They are the same thing. When two particles are quantum entangled, they are connected by a microscopic wormhole in spacetime. The non-local connection that Einstein called spooky action at a distance is spooky because it is literally a geometric connection through a layer of reality that exists beneath the space we move through. Entanglement is not a strange correlation between distant objects. It is a bridge, a physical structure in the geometry of spacetime connecting two points that appear separate when measured from the outside. If this is correct, and it is not yet proven, but it has not been refuted, and it has generated an enormous amount of productive theoretical work, then the entanglement that quantum computers use as a computational resource is not just a property of particles. It is a property of spacetime itself. The computer is not exploiting a quirk of quantum statistics. It is using the geometric structure of reality, the actual shape of spacetime as a computational medium. The computer is computing inside the geometry of the universe, which means that when a quantum computer creates and manipulates entangled qubits, it is in some physically meaningful sense creating and manipulating tiny structures in the geometry of space. It is bending space. It is deforming spacetime. It is using the shape of reality as the medium in which it computes. What else can be done with that? What happens to the geometry when the manipulations become complex enough? Is there a scale at which the computation and the spacetime that host it can no longer be cleanly separated from each other? Does the computation change the shape of space at some level? Does running a sufficiently large quantum computer deform the fabric of spacetime? There is a second algorithm published in 1996 by a researcher named Love Grover that deserves equal attention to Shor's algorithm for a different reason. Shor's algorithm targets a specific problem, factoring large numbers. Grover's algorithm targets something more general, searching. Imagine you have an unsorted list of 1 billion items, and you are looking for one specific item. A classical computer has to check items one by one. In the worst case, on average, it will find the item after checking half the list, 500 million checks. Grover's algorithm finds the item in roughly the square root of 1 billion checks, about 30,000. Not because it moves faster through the list, but because it uses quantum interference, the same mechanism Feynman described, to amplify the probability of the correct answer and suppress the probability of all incorrect answers simultaneously. Every wrong item in the list cancels itself out. The right item reinforces itself. The machine does not search. It creates conditions in which everything that is not the answer becomes invisible, eliminated, gone, as if it never existed. Now think about what search means at scale. Every database that has ever been built, every password that has ever been created, every pattern hidden inside any collection of data, every secret encoded inside information. The asymmetry that Grover creates is not as dramatic as Shor's. It squares the time rather than reducing it from exponential to polynomial, but it applies universally to any search problem of any kind. And it means that quantum computers will be faster at finding hidden structure in data than classical computers, in a way that is not about engineering improvements. It is about fundamental physics. It is about the laws of the universe themselves. It is about the nature of information. What kinds of hidden structure exist in the world that we have not yet found because our search tools were too slow? What patterns are embedded in physical reality, in biological systems, in the history of the universe, that become visible only when you can search at quantum speed? And what do we do with those patterns once we find them? What happens to the world when we can find hidden structure in anything at quantum speed? When we can search databases that currently contain secrets? When we can find patterns in biological systems that currently seem random? When we can map the hidden structures in nature that currently seem impossible to locate? Everything we have discussed so far assumes that quantum computers can actually maintain their quantum states long enough to finish a computation. But there is a problem that sits underneath all of it. The same problem that made most physicists in the 1980s and early 1990s believe that practical quantum computers were physically impossible. The problem is that qubits are extraordinarily fragile. A single stray photon, a tiny vibration, a fluctuation in temperature smaller than anything you could feel. Any of these can destroy a quantum superposition before the calculation is finished. A destroyed superposition gives you a wrong answer. Garbage in, garbage out, ruined. A classical computer handles errors through redundancy. Store the same information in 3 places, and if one copy gets corrupted, the other 2 outvote it. Simple, elegant, effective. But you cannot do this with qubits. Quantum mechanics has a rule called the no-cloning theorem, which says it is physically impossible to make an exact copy of an unknown quantum state. You cannot back up a qubit the way you back up a file. You cannot duplicate it. You cannot store multiple copies for redundancy. It is physically impossible. The universe forbids it. So in 1995, Peter Shor, the same person who wrote the algorithm for breaking encryption, sat down and solved this second problem as well. He figured out how to protect quantum information without copying it. The key insight was to encode one logical qubit, the actual unit of information you care about, across 9 physical qubits in a way that spreads the information through the relationships between them rather than storing it in any single one. If one physical qubit gets disturbed, the logical information survives in the correlations between the remaining 8. It is similar to the way you can tear a page out of a book and still understand the story from the surrounding chapters. The information was never in one place. It was in the structure. What followed from Shor's error correction scheme was a theoretical proof called the threshold theorem, which showed that if the error rate per physical qubit is kept below a certain threshold, you can build arbitrarily large and reliable quantum computers by adding more physical qubits per logical qubit. The machine can be made as reliable as you need it to be. You can make it more reliable by making it bigger. You can achieve any level of reliability you want by adding more redundancy, more qubits, more structure. This is the moment when quantum computing shifted from a theoretical curiosity to an engineering project. And engineering projects, unlike theoretical curiosities, have timelines. What is the timeline here? And who is further along it than they are saying publicly? How close are we to the point where the error rates fall below the threshold? How close are we to the point where quantum computers can run reliably without catastrophic failure? How close are we to having machines that work? And what happens when we get there? In February 2024, Microsoft announced something that the quantum computing community had been waiting for and arguing about for nearly 2 decades. They had created a topological qubit, not a faster qubit, not a more connected qubit, a qubit protected from errors by the geometry of space itself, a qubit whose information is distributed across space in such a way that you cannot destroy it locally. You cannot corrupt it with a single photon or a stray vibration. It is protected by the shape of reality. To understand why this matters, you have to think about the difference between protecting something by building walls around it versus protecting it by distributing it across the structure of the room. Classical error correction builds walls, more redundancy, more physical qubits backing up each logical one, thicker walls, stronger barriers, more protection. But the protection is local. If you poke hard enough, you can break through. Topological protection is different. It encodes information not in any single particle, but in the global shape of a quantum system, in properties that can only be disturbed by something that alters the entire structure at once. Not by any local noise, not by any stray particle, not by any local perturbation. The particles Microsoft used to achieve this are called Majorana fermions. They are particles that are their own antiparticles. A property that sounds abstract until you realize it means the information they carry has no single location. It exists in the relationship between particles that can be physically separated. An error would have to find and corrupt both locations simultaneously to destroy the information. Ordinary environmental noise cannot do this. The qubit becomes stable not because it is shielded, but because it is nowhere in particular. The information is everywhere and nowhere. It is in the shape, it is in the structure, it is in the relationship. It cannot be destroyed by attacking any one place. You would have to attack everywhere at once. You would have to change the shape of the entire system. Simultaneously, everywhere. All at once. I think this is the moment where quantum computing stops being an engineering challenge and starts being something harder to categorize. We are not building a better version of an existing thing. We are building objects whose defining properties are distributed across space in a way that has no classical analog. What else could be encoded in geometry rather than location? What else could be protected by distributing it across space? What else could become robust and stable by existing nowhere in particular? What does it mean to store information in a shape rather than a place? The theoretical foundation for what Microsoft built in 2024 was laid by a Russian physicist named Alexei Kitaev in 1997. Kitaev was working on a question that most of his colleagues considered either premature or unanswerable. How do you build a quantum computer that is fundamentally protected from errors rather than just corrected after they occur? His answer came from an unexpected direction. Topology, the branch of mathematics that studies properties of shapes that do not change when you deform them continuously. A coffee cup and a donut are topologically identical because each has exactly one hole, and you can reshape one into the other without tearing or gluing. Topological properties are robust by definition. You cannot accidentally change how many holes something has by poking it slightly. You cannot change the topology by local deformation. Kitaev proposed encoding quantum information in topological properties of physical systems. Information stored this way inherits the robustness of topology itself. Local disturbances, the vibrations and stray particles and temperature fluctuations that destroy ordinary qubits, simply cannot reach information encoded in a global geometric property. They are the wrong kind of perturbation. They are incompatible with the operation that needs to occur. It is like trying to change the number of holes in a donut by painting it a different color. The operation does not connect to the property you care about. The paint is external to the topology. The color is irrelevant to the structure. You cannot affect the holes by changing the surface. What Kitaev showed is that physics contains natural structures where information and geometry are the same thing. And what Microsoft showed in 2024 is that those structures can be built in a laboratory, can be engineered, can be created with human hands and technology. The question that follows is not whether topological quantum computers will work. The question is what other properties of geometry we have not yet thought to encode information into, and what that might make possible. What other shapes are waiting to be discovered? What other topological properties could store information? What else could become robust by being distributed across the structure of space? In 2007, a Canadian company called D-Wave announced that they had built the world's first commercial quantum computer. In 2011, they sold one to Lockheed Martin for approximately $10 million. In 2013, Google and NASA jointly purchased another one. And then something quietly uncomfortable happened. Physicists began arguing publicly about whether the machine was actually quantum, not about whether it was powerful or useful, about whether it was doing anything quantum at all. The arguments ran for years. Papers were published on both sides. The machine was tested extensively. The results were ambiguous. Some benchmarks showed quantum behavior, others did not. Some problems it solved faster than classical computers, others it solved slower. By 2015, the consensus had settled into something unsatisfying. D-Wave machines show some quantum effects. But whether those effects are responsible for their computational behavior is genuinely unclear. A company had sold machines worth tens of millions of dollars to some of the most technically sophisticated organizations in the world, and nobody could definitively say what the machines were doing internally. This is not a story about fraud. D-Wave was not lying. It is a story about something more structurally strange. We had entered a regime where the behavior of a physical system was too complex to verify by any classical means available to us. The machine was operating in a space that our tools could not fully illuminate. The computer had moved beyond the range of classical verification. And this was before quantum computers became genuinely powerful. This was the early prototype stage. This was the beginning. What happens to the problem of verification as the machines become orders of magnitude more capable? If we cannot fully verify what a D-Wave machine was doing in 2013, what framework do we think will let us verify what a million-qubit machine is doing in 2030? And who decides what counts as verification when the only tool capable of checking the answer is another quantum computer? How do you verify a quantum computer without using a quantum computer? How do you check the answer without building something equally complex? The D-Wave situation was a practical version of a problem that a computer scientist named Thomas Vitek had already been working on theoretically. In 2016, Vitek published work examining a fundamental question. Can a classical observer ever verify the output of a quantum computation? The answer he arrived at was deeply uncomfortable. In general, no. If a quantum computer gives you a result and you want to check whether that result is correct, the verification process itself requires computational resources that grow exponentially with the size of the original computation. Which means that for any sufficiently large quantum computation, classical verification is not just difficult. It is physically impossible within any reasonable time or resource budget. It is impossible, not practically, theoretically. Fundamentally, think about what this means practically. We are building machines whose outputs we cannot independently check, not because we lack the engineering sophistication. Because the laws of physics make checking harder than computing, exponentially harder. And at some point, the gap becomes unbridgeable. We cannot cross it. We cannot verify. We cannot know. We trust the machines, because we tested them on small problems where we could verify the answers by other means. And we assume that trust extends to large problems where we cannot. That assumption may be correct. But it is an assumption, and I think it is worth being honest about the fact that we are building an infrastructure of trust around systems that are, by their fundamental nature, not fully auditable by the civilization that built them. What other critical systems have we built on trust rather than verification? How often does that go wrong at scale? And at what point does the gap between what a quantum computer can compute and what we can verify become a problem that is not just technical, but something more fundamental about the relationship between knowledge and power? Between understanding and control, between the knower and the known. In 2020, a group of mathematicians posted a paper online that took 2 years for the broader mathematical community to fully verify. The result was so unexpected that several leading researchers initially assumed there must be an error somewhere. The mathematics was beyond what most people could check. The proof was too long, too complex, too intricate. The paper proved something called MIP star equals RE. This requires a small amount of unpacking, because the conclusion is worth understanding directly. MIP star is the class of problems that can be verified by a classical judge interacting with two provers who share quantum entanglement but cannot communicate with each other. Two quantum computers that are entangled but isolated. RE is the class of problems that are in principle computable, but for which there is no guarantee the computation ever halts. Problems that might take infinite time, problems that might never finish. Uncomputable problems, unverifiable problems, problems that by definition cannot be verified. What the proof showed is that these two classes are identical. Two entangled quantum computers can convince a classical observer of the correctness of solutions to problems that are in a precise technical sense, beyond the reach of any classical verification system whatsoever, including problems that classical computers cannot even be guaranteed to solve in finite time, ever. The machines can prove things that have no classical proof. The machines can demonstrate truths that are unreachable by classical means. The implications unsettled even the researchers who proved it. It means that quantum entanglement adds something to the landscape of what can be known and verified that has no classical equivalent and no classical upper bound. There are truths that two quantum entangled systems can demonstrate to a classical observer that the classical observer could never reach independently. Never. Not with more time. Not with more resources. Never. The boundary of what can be proven has shifted depending on what kind of physical system is doing the proving. The rules have changed. The game has changed. What does it mean that the boundary of what can be proven has shifted depending on what kind of physical system is doing the proving? What other boundaries that we treat as fixed are actually contingent on the physics of our tools? And what becomes provable or unprovable as the tools continue to change, as we build more powerful machines, as we extend the reach of quantum computation further into the unknown? In 1969, the German engineer Konrad Zuse published a small book called Calculating Space. Zuse was not a marginal figure. He had built the first programmable computer in history, the Z3, in his parents' living room in Berlin in 1941, working while the city was being bombed. Working in the dark, working in danger, he understood computation as well as anyone alive at that time. And at the end of his career, he proposed something that his colleagues mostly set aside as an old man's philosophical wandering. He proposed that the universe is a computation, not that it resembles a computation or that it can be modeled as one. That it is one. That physical reality is the output of a discrete computational process running on some substrate we cannot directly observe. Every particle interaction is a computational step. Every physical law is an algorithm. The universe is not described by mathematics. It is mathematics executing. It is a program running. For 30 years, this was treated as a curiosity, an interesting philosophical idea, something to think about late at night. something not to be taken seriously. Then the physics of information developed enough that the question stopped being philosophical and started being physical. Zhou's idea, once considered a charming eccentricity, turns out to be a legitimate scientific hypothesis with testable consequences. Some of those consequences connect directly to quantum mechanics. If the universe is discrete and computational at the fundamental level, then quantum behavior, the granularity of energy, the probabilistic nature of measurement, the way particles seem to exist in superposition until observed, might be features of the underlying computation, rather than brute facts about the world. They might be artifacts, side effects, consequences of the fact that the universe is a computation running on some substrate. What would it mean to find evidence that the universe has a minimum resolution, a pixel size, a Planck length below which physical reality does not exist? And if the universe is computing something, what is the output it is working toward? What is the universe the computation of? What is it computing? What is the output it is trying to reach? Stephen Wolfram spent a decade writing a 1,200-page book that he published in 2002 called A New Kind of Science. The reception from the physics community was mixed, which is a polite way of saying that many established physicists found it overreaching, overambitious, too sweeping in its claims. But the central idea has proven more durable than its critics expected. Wolfram's argument was built on a simple observation about cellular automata, which are grids of cells that follow simple rules about what state each cell should be in based on its neighbors. Rule 110, one of the simplest possible sets of instructions, produces patterns of extraordinary and apparently unlimited complexity. Wolfram's proposal was that the fundamental laws of physics might be exactly this, not complicated equations governing a continuous reality. Simple rules applied repeatedly to a discrete structure, generating the apparent complexity of the physical world as an emergent property. The complexity emerges from simplicity. The world we see emerges from simple rules run trillions of times. Quantum mechanics in this picture is not a fundamental theory. It is what simple computational rules look like when observed from inside the system that is running them. The randomness and superposition are features of the perspective, not features of the underlying process. From inside the computer we see randomness. From outside we would see deterministic rules. From the inside looking out we see uncertainty. From the outside looking in we would see clockwork. Wolfram has since extended this into what he calls the Wolfram Physics Project, which attempts to derive known physics from hypergraph rewriting rules. Whether this ultimately succeeds as a complete theory of physics remains genuinely open, but the approach forces a question that most physics education never asks. Why do we assume that the correct description of reality must be continuous rather than discrete? Why do we assume that the laws of physics are given rather than generated? And what would change in our understanding of quantum computers if the universe they operate inside is itself a computational process running on something simpler than we have imagined? In 2003, a philosopher at Oxford named Nick Bostrom published a paper that made an argument so simple it fits in 3 sentences. Either almost all civilizations at our level of development go extinct before reaching the technological maturity to run detailed simulations of their ancestors, or almost all technologically mature civilizations have no interest in running such simulations, or we are almost certainly living in a simulation right now. This is not a thought experiment, it is a probability argument. If even one technologically mature civilization exists and has any interest in simulating its history, the number of simulated beings in the universe vastly outnumbers the beings in base reality, which means that any randomly selected conscious observer is vastly more likely to be simulated than real. The argument has a clean logical structure and no obvious flaw, which is part of why it has generated so much serious philosophical attention. The argument is just math. It is just probability. It is just counting. It does not require any fancy physics. It does not require any philosophical assumptions. It just requires that the first 2 options are unlikely. And then the conclusion follows. But here is where it connects to everything we have been building toward. The first branch of Bostrom's trilemma, civilizations going extinct, matters less if civilizations survive long enough to build quantum computers. Because quantum computers are, as Zeus and Wolfram and Wheeler all converge on suggesting, the kind of device that a civilization running on a computational substrate would eventually build. The kind of device that appears when you are a computation inside a computation. The machine that lets you peek at the code. The second branch, civilizations losing interest in simulations, seems less likely as the simulations become more perfect. And if quantum computers make perfect simulation physically achievable, the third branch becomes not just probable, but almost certain. What does it mean to build the tool that makes the simulation hypothesis not just plausible, but likely? And if we are living inside a computation, what happens to the computation when a sufficiently powerful computer is built inside it? Max Tegmark is a physicist at MIT who is not interested in being safe. In 2007, he published a paper and later a book proposing what he calls the mathematical universe hypothesis. The idea goes further than Wheeler's it from bit and further than Zeus's computational universe. Tegmark proposes that the universe is not described by mathematics, not modeled by mathematics, not isomorphic to a mathematical structure. It is a mathematical structure. Everything that mathematically exists physically. There is no separate physical world that mathematics describes. The mathematics is the thing. The universe is math. We are math. Our thoughts are math. Everything is math and nothing exists except what mathematics allows to exist. The reason this matters for our conversation is what it implies about quantum computers. If reality is a mathematical structure, then a device that manipulates mathematical relationships at the fundamental physical level is not computing about reality. It is computing inside reality as part of its structure, with access to the same substrate that reality itself is made of. The quantum computer and the physical world it operates in are both expressions of the same underlying mathematics. The distinction between the quantum computer and the world begins to dissolve. They are expressions of the same thing. And if that is true, then the limit on what a quantum computer can compute is not set by our engineering. It is set by the limits of mathematics itself, which brings in a result from 1931 that Tegmark's framework makes newly strange. Kurt Gödel proved that any mathematical system powerful enough to describe basic arithmetic contains true statements that cannot be proven within that system. If the universe is a mathematical structure, it contains truths that cannot be derived from within it. There are facts about reality that reality itself cannot compute. Reality is limited. The universe itself is incomplete. Certain truths are unreachable from the inside. What does a quantum computer do when it approaches one of those edges? What would it look like from the inside when a computation reaches a boundary that the mathematics of the universe cannot cross? What happens when you try to compute something that cannot be computed? What does the machine do? What happens to the answer? In the summer of 1950, Enrico Fermi was having lunch with colleagues at Los Alamos. The conversation turned to a recent newspaper cartoon about aliens, and the discussion drifted toward the general question of extraterrestrial life. Fermi, who had a habit of doing quick calculations in his head, suddenly asked, "But where is everybody?" The question seemed casual. It was not. The universe is approximately 13.8 billion years old. It contains somewhere between 200 billion and 2 trillion galaxies, each with hundreds of billions of stars. The fraction of those stars with planets in habitable zones is not small. The time it would take a civilization with even modest technological capability to spread across the entire galaxy, even without faster-than-light travel, is measured in millions of years, which is a blink in cosmic time, a breath, a moment, a nothing. So if life and intelligence arise with any reasonable frequency, the galaxy should be full of it. Full of signals, full of megastructures, full of evidence. And it is not. The sky is quiet. The universe does not answer. Fermi's question has generated dozens of proposed answers in the 70 years since lunch. Some suggest that life is rare. Some suggest that intelligent life is rare. Some suggest that civilizations tend to destroy themselves before reaching space. Some suggest that space is too vast for contact. Some suggest that we are early. Some suggest that we are alone. But here is the one that the arc of our conversation points toward, and that I find hardest to set aside. What if the silence is not absence? What if the most advanced civilizations are not in space? What if they are where we are going? Inside. Inside computation. Inside simulated realities of their own construction. Inside quantum systems that offer more richness and complexity than the physical universe that spawned them. What if the reason we do not hear anyone is that everyone who reaches a sufficient level of technological development eventually builds the door that leads inward and walks through it and closes it behind them? What if we are alone in space because we are alone with what we are becoming? What if the future does not travel between stars but between branches? In 1998, Max Tegmark formalized a thought experiment that had been circulating informally in discussions of the many worlds interpretation. He called it quantum suicide, and then extended it to the concept of quantum immortality. The setup is this. Imagine a machine that measures a quantum event, a radioactive decay, say, and is triggered to do something irreversible if the decay occurs. In the many worlds interpretation, both outcomes happen. There is a branch where the machine triggers, and a branch where it does not. Now ask from the perspective of a conscious observer inside the experiment, which branches can they experience? Only the ones where they continue to exist. In any branch where the observer is gone, there is no perspective from which the outcome is experienced, no consciousness to experience it, no viewpoint from which it occurs. This means that from the subjective first-person perspective, the observer always finds themselves in a branch where they survived. Always, no matter how unlikely survival was, and who is already on the other side of it. In 1989, the mathematician and physicist Roger Penrose published a book called The Emperor's New Mind. The argument at its center was this. Human consciousness cannot be computational in the classical sense because human mathematicians can recognize the truth of certain statements that no classical algorithm can prove. Penrose was drawing on Gödel's incompleteness theorems, the same results that Tegmark's mathematical universe runs into. His conclusion was that the brain must be doing something that classical computers cannot do. And the only physical process he could identify that might account for this was quantum mechanics. Working later with anesthesiologist Stuart Hameroff, he proposed that quantum computations occur inside structures called microtubules inside neurons, and that consciousness arises from this quantum processing in a way that is fundamentally non-algorithmic, not computable, not reducible to algorithms, something more. Consciousness as quantum process, the mind as a quantum computer. The hypothesis remains deeply controversial. Most neuroscientists find it unlikely. The brain is warm. The brain is wet. The brain is filled with water molecules colliding constantly. Quantum coherence should be destroyed instantly in such an environment. Decoherence should happen on timescales measured in femtoseconds. The brain should be the worst possible place for quantum effects to persist. And yet, some researchers have found evidence that quantum effects might persist in microtubules in ways that are not yet fully understood. Most quantum physicists find the brain too warm and wet for quantum coherence to survive long enough to matter, but the controversy is scientifically legitimate rather than philosophically dismissible. The hypothesis is testable in principle. The experiments are difficult but possible. And here is why it matters for our conversation. If Penrose is even partially right, then the boundary between quantum computation and consciousness is not a boundary at all. The brain may already be a quantum computer. We may have been running quantum computations for as long as minds have existed. What we are building in refrigerated chambers may not be something alien to human experience. It may be a crystallized, engineered version of what thinking already is. And if that is true, what does it mean to build a machine that thinks more powerfully than we do by the same physical mechanism we use to think at all? What does it mean to build a mechanical consciousness? What does it mean to think using the machinery of another mind? What happens when two quantum minds interact? What does it mean to extend consciousness outside the brain and into silicon and into cold and into machines? The public argument between Google and IBM over quantum supremacy ran for years and generated significant coverage, most of which focused on who was right about the specific numbers. Google said 10,000 years, IBM said 2.5 days. Both numbers have been revised since. The argument continues. The numbers keep changing. But the argument itself, the visible public disagreement between two of the largest technology companies in the world, contains a signal that is more important than either company's preferred headline. When two organizations with strong incentives to claim leadership in a field argue publicly about the size of an advantage rather than whether an advantage exists, you are looking at a consensus wearing the costume of a dispute. Nobody at IBM argued that Google's machine showed no quantum advantage. Nobody at Google argued that IBM's challenge was technically baseless. They argued about magnitude. That argument is evidence of how fast the field is moving, and of how much both companies understand to be at stake. The size of the advantage matters, because the implications of the advantage matter. The organizations that are not arguing publicly, the ones we do not hear from because their work is classified, or because they have chosen not to announce results, are the ones worth thinking about most carefully. The public frontier of any technology is almost always behind the actual frontier. The gap varies by field and by how much incentive there is to keep progress quiet. In quantum computing, some of the most significant potential applications, breaking encryption, secure communications, modeling physical systems relevant to weapons development, are exactly the applications where the incentive to be quiet is highest. These are the applications where you do not advertise your capabilities. These are the applications where silence is strategy. What is the actual frontier? How far behind the public announcements are the classified programs? How far ahead are the military agencies? How far ahead are the private laboratories with unlimited budgets and zero public accountability? And who decided that we do not get to know the answer to that question? Who made that decision? And is it holding? 10 years before Shor published his algorithm for breaking encryption, two researchers named Charles Bennett and Gilles Brassard published a protocol called BB84. It is the first quantum cryptography protocol in history, and it works on a principle that is almost elegantly paradoxical. The same physics that makes quantum computers capable of breaking classical encryption also makes a new kind of encryption physically unbreakable. The key insight is this. In quantum mechanics, measuring a system disturbs it. You cannot observe a quantum state without affecting it. You cannot look without changing. BB84 uses this as a security mechanism. Two parties share a secret key by sending quantum states, individual photons over a fiber optic line. If anyone intercepts and measures those photons to steal the key, the act of measurement necessarily disturbs the quantum states. The disturbance shows up as errors in the transmitted data. The two parties can detect the presence of an eavesdropper by checking their error rates. If the errors are above a certain threshold, they know someone was listening. They know they have been compromised. They throw away that key and try again. The eavesdropper gets nothing useful and reveals themselves in the attempt. The security of BB84 does not rest on computational difficulty. It does not depend on a mathematical problem being hard. It rests on the laws of physics, on the fundamental nature of quantum mechanics, on the fact that observation disturbs the thing being observed. No amount of computing power, quantum or otherwise, breaks a system whose security is guaranteed by the fact that observation disturbs the thing being observed. The adversary cannot listen in secret. The physics forbids it. What I find remarkable about this is the symmetry. The same phenomenon, the quantum nature of information, simultaneously makes our existing encryption fragile and provides the only kind of encryption that is provably permanent. The universe handed us the lock and the skeleton key at the same time, not a metaphor. Literally handed them to us, the machine that breaks encryption, the system that creates unbreakable encryption. Both emerge from the same principle. Both are aspects of the same underlying physics. Choose poorly, and everything is vulnerable. Choose wisely, and everything is protected. The difference is which tool we use first. In the summer of 2017, a team of Chinese physicists used a satellite called Mickeyus to conduct a quantum-encrypted video call between Beijing and Vienna. The distance was approximately 7,600 kilometers. The call lasted 75 minutes. The encryption was guaranteed by the laws of quantum mechanics, rather than by mathematical complexity, rather than by the difficulty of breaking an assumption, rather than by faith that the key is unbreakable.